Okay? Where else did you do this kind of nonsense? The only way you remember stuff in life is to connect everything so that until you become fully dementia driven, you will remember something. If you remember a little piece, it will fall through the cracks of your brain. So connect everything you know into one big huge mess, then it will stay. So where else did you learn this kind of nonsense about taking like a coin, throwing it up and deciding if it comes this way, do one, otherwise what? Exploration and exploitation. This is not a new idea. You could have done something like this. In essence, you are saying it's being used for a different purpose here. Essentially, this P basically is being used to decide, whether or not the networks, whether or not a weight is considered to be present or not. And just like in the exploration exploitation, the probability P what could be changed over your lifetime so that towards the end of your life you are greedy because there's no more time to learn, might as well enjoy the money you made, right? You could do this here too. That would be an improvement over dropout. So in learning the network, you essentially, every time you're only updating some subset of weights. Some subset of weights. So it's as if you are, within this one network configuration, you are actually learning exponential number of different networks. They're all sort of fused into this one network. So in the test case, you just use this one network. So testing is still cheap. Bayesian problem typically is during the testing time, the baby is saying, let me figure out, I have 29 million hypotheses about how to classify this. According to this one, this is the bus, according to this one, this is the frog, and you're dead. Okay? Here you're saying I just have one network. During the training, I just avoided jumping to the conclusions by essentially updating subsets of the weights, random subsets of the weights. Beautiful idea. That's why it got patented. It wasn't actually done in Google. They bought the guy who did it and patented it. There's this Indian student working with Jeff Hinton did this idea in Toronto. And then one day Jeff Hinton was minding his own business and Google swooped in and said, your company, which you haven't yet started, has been bought. I said, okay, I didn't know I had a company. Okay, bought. So that's how dropout happened. But dropout is not coming out of nowhere. Neither of any of the ideas in neural networks, none of the ideas in neural networks are coming out of a vacuum. They're coming out of a fertile area of foundations of machine learning. For people who don't understand that, each of these look like individual ideas that just depend on somebody's genius. No. Genius is trying multiple ideas, one day one thing works. The real question is where do you get your ideas? In fact, there's this beautiful statement that, what's his name? The guy who got, one of the guys, I forgot his name unfortunately. There's this guy who got 2 Nobel Prizes. And there are only very few of them. One of these guys, I forgot his name. So he was asked, how did you get such good ideas that you got 2 Nobel Prizes? He said, I have lots of ideas. I throw away the bad ones. That's the definition of genius. Genius doesn't mean you have one idea. Genius means you know how to create ideas and throwing out the bad ones. If you're a one-trick pony, you are not a genius. Okay? So that's dropout. And as I said, please don't. The next one naturally gets us into a third way of dealing with learning and bias, which is basically these two, regularization, randomization during learning, are two of the ideas. The third idea is change the form of the function that you are learning. In the case of neural networks, that sort of becomes change the architecture of the network. Up until now, you looked at one specific architecture, essentially the fully connected network. There's a bunch of nodes. Every one of them is connected to every node in the next layer. Every one of them is connected to every node in the next layer, and so on and so forth. That's basically your architecture, which also means you have huge number of weights. Right? If you have m nodes here, n nodes here, you have m times n connections. That means each of them needs a weight. So there are m times n weights. Remember that picture from, what's his name, 3 blue, 1 brown? That little thing had what, 13,000 parameters. Because it's a dense network and you're just multiplying, number of nodes in layer 1 to number of nodes in layer 2. You want to start reducing the number of parameters. That's the next idea. And that's what gets us to convnets. And in particular, basically, I want to show this to you so that the people who leave at least know where to start looking from. In essence, rather than have a network like this, which everything is connected to everything in the next layer, you will, in essence, try to say many of the weights are the same. Many of the weights are the same. So the weights are being reused many, many times. And in particular, the weights being used are dependent on the size of the region. And then as the region goes next, you use the same weights for that region, that region, that region. So if you think in terms of this kind of network, rather than making every one of these weights different completely, act as if you only have 15 weights. And those 15 weights kind of time share. Here I'll put it first, then here, then here, then here. If you do that, then you suddenly went from m times n to a much smaller number that you decided. This reduces the expressiveness of the function, because everything that can be learned by this compressed function can also be learned here. But if your data has regularity, and this crazy thing you did winds up being good with respect to the structure of your data, you win big time. In vision, it turns out in general that basically neuroscience has already told us that the way our retina works is it basically has these saccades. By the way, I don't know how many of you realize this. As you are seeing the world, you're taking little pieces and the brain nicely connects them all into a single reality, which is exactly why magic is possible. You think you're seeing everything, but you're not seeing half the things. Okay, but this is done in human vision, and so basically one of the ideas was to copy this idea to the way neural networks are implemented, sort of approximately. And what you wind up doing here, this yellow thing that's moving, essentially, that yellow thing is put here. So it's basically, it's called a filter. It's saying, for this region, I have these weights, this weight, this weight, this weight, these. So 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. What I'm going to do is I multiply the inputs, which are in the bold black, by these weights, sum them up. If you do this, 1 times 1, 1, plus 0, plus 1 times 1, 1, 2, plus 0, plus 1 times 1, 3, plus 0, plus 1 times 0, 0, plus 0 times 0, 0, plus 1 times 1, 1, 3 plus 1, 4. So I put 4 here. Okay, I'm going to basically let people who need to go somewhere go for a second, and then we'll continue. Okay, so this is basically what we'll be doing in the extended session about convnets. Okay. Yeah, what's your question?
How do you connections have you been using in the past?
That anytime you need, okay, hello, put up. So the question, in fact, all important question was already asked in the very first minute of this SectionNet session. Who gives these numbers in the red? Whoever gives us any numbers that we ever need. The rich but extremely slow uncle. Gradient descent. So what you'll wind up doing is these are essentially weights. They just don't look like weights because you put them in this sort of a kernel. But again, I think for a image, it looks basically, an image is typically like a two-dimensional thing. You think of it as a square, and the kernel is like a small square that's sort of moving over it. But really, the important thing to understand is instead of making every node here be connected to every other node here with a completely different set of weights, what we are trying to do is there are only like 15 weights. And basically the weight, instead of all these connections, the connections are sort of connecting nodes and moving up. Can you visualize that? It's like as if there's a bunch of connections. It's like a bunch of wires, and normally everything here is connected to everything here with different sets of wires. Instead now, I just have 8 wires. I take the same 8 wires, connect them everywhere. Do you see what I'm saying? Now of course, wires have resistance. The resistance is the weight. This is, by the way, the most important question that most people don't understand. Again, in general, as I said, in the old days, people who would actually say they know AI are the only ones who have actually taken intro to AI or something. Now, in fact, it's more like an albatross to actually sit down and take a course, because you should do machine learning in 2 hours or less and get your job right away. Okay, so most people have no idea when these things are coming. Again, I'm not talking about Jeff Hinton. That guy knows, thankfully. But he's not the only guy doing this stuff. Everybody else thinks they're an expert. We're not as good as Jeff Hinton, but we are good enough. Unfortunately, most of them are bozos. Okay, and so we're trying to improve your level. Right? Okay, so that's a very good question. These are the weights. Think of the kernels as the weights. The important thing is, if in fact, think of this, if you're doing a fixed, fully dense network, then what it would look like is, all these inputs are connected to, each of them are connected to a different node. That means 1, 2, 3, 4, 5. 5 times 5, 25. So there are 25 nodes in the first row. They would then be connected to another 25 nodes in the second row if you decide to do so, another 25 nodes in the third row. And at each level, 25 times 25, which is 625 different weights are being learned. It's so general that it, of course, subsumes the case where all 625 weights are just the copies of these 9 weights. But you would figure it out very slowly. Here you're saying, I'm just going to assume the weights are connected. By the way, one of the beautiful things is the notion of convolutional networks, even though we're presenting it first, when we get to relational learning, and if you think of things like Bayesian relational models, relational networks, they do the exact same idea. They basically reduce the number of weights by saying the same weights are being shared. The terminology used is these weights are being shared. Instead of 625 weights, I'm just getting by with 9 weights, which will just move around, connecting it to everybody. I'm trying to look like that yellow thing. Okay, I'm also moving. You see what I mean? That's what ConvNet is doing. But these weights, I still don't know what they are. Just like I didn't know 625. Interestingly, remember, you never would have asked, who would have given the weights here? You don't mind making 625 weights by your slow rich uncle, right? But the slow rich uncle will be extremely happy. They only have to make 9 weights. And there's a lot more data now because different regions act as different pieces of the data. Yes?
How do we decide like the size of this kernel? Like how
Yeah. This is all engineering. This is what we'll do for the rest of the class. I mean, not rest, whatever. It's like, again, there's a huge amount of tricks of the trade. But what I'm trying to make sure you understand is where the tricks come from. You can buy a Cliff's Guide for neural networks, which will tell you some of these things that I'll be telling you for the rest of the time. But it's extremely important to understand what's going on here, which is the shared weights. Yes?
At each and every layer we have a different kernel or the same one that's shared across the...
No, you can, so every kernel is called a filter. The terminology is every kernel is called a filter. You can have as many filters as you want at each layer. In fact, if you apply, let's say, one filter, this filter to this image, you get this thingy. It's not called image, it's a thingy. Okay? If I have 2 filters, I'll get 2 of those thingies. If I have 15 filters, I'll get 15 of these thingies. So in fact, what you're getting is image volumes, not images. I mean, if you think of this as some sort of an intermediate image, you're not getting images, you're getting image volumes. Each volume being produced by a filter. Here is a way of thinking about it. Initial input image itself has 3 layers. RGB. So there was the God's own image, and the R filter only takes the red intensity values, puts it in one layer. The G filter takes the green intensity values, puts in the second layer. And the blue filter takes the blue intensity values, puts in the third layer. And these 3 together you will be able to reconstruct the image. In this particular case, in essence, these are intermediate filters. RGB are well-known filters. These are intermediate filters. The interesting thing about why these are called filters is of this picture, is because of this picture. Image processing was full of hand-coded feature recognition, hand-coded features. And the features that they would do would be these kernels. And each of these kernels, for example, this one will sharpen the image. This one will detect edges. This one is basically, of course, identity function. That means it's taking a region of pixels and it's trying to kind of do operations on them. The top one is called identity because in the region of the pictures, it basically just takes the middle picture. And if you put this filter at every point such that every pixel gets to have the chance of being the center of the photo, then you get the same image back. That's why it's identity transformation. Each of these basically are called filters. Like for example, this is a box-Bullard filter, this is a Gaussian bar filter. There are filters named after people, like Gabor filter. Okay, and then what is the other one? There's this Gabor filter, there's blue filter is a data structures thing, but Gabor filter. This is how image processing used to work. Okay, they would apply these and then get some features and then basically give those as the inputs to the under-parameterized low-dimensional neural networks. Okay, instead what you're doing now is, in the beginning until about 2013, people would take these kinds of filters. So for example, the weights would be decided by some named guys, and you have to keep giving them patent values, patent dollars. Okay, and then they will use them to extract the features and then do some sort of a neural network or something else. What we do now is we realize these are just weights. These are unnamed filters, just like unnamed functions. Computer scientists know this. Lambda functions are unnamed functions. Code can generate functions. Code here is generating filters. You just decide how many filters you want. I'll take care of what they should be. That's basically what we are saying. You see what I'm saying? How many filters, etc.? These are engineering issues. You can put some number of filters. So for example, I mean, I'll get through that in a minute, but so this is the word, the filters come from that. Okay? So the normal convolutional layers, convolutional networks have been tried lots and lots of different architectures, but this is sort of the standard architectures lots of people use. Again, actually, this is from Karpathy's slides. So you would have a convolutional layer, which basically, for example, which will have a bank of filters that are being applied to the input at that layer to generate an image volume, which is why notice the image volumes. A volume is basically each filter gets you a layer. If there are k filters, there are k layers. K layers is a k size volume. Okay? That is basically one part. And the second part that they do is, of course, you have to, here is a question. This operation of kernels, is this linear or non-linear? It's linear. It's just weight times input plus it times input plus weight times input. Again, remember that what is happening here is like saying I have like some set of wires and I'm taking those wires, the same three set of wires here first, then here, then here. If you can visualize this, you understood what convolutional networks are doing. It's just the same thing. It's just that images are rectangular, so you tend to think in terms of rectangular. You could have made the images to be raster scan, that would be fine. It would look as if this guy would be next to this guy, because in the raster scan, it will go like this, right? But I'm essentially saying that's how you will connect these 8 weights that you're using. You're going to connect them in different places and compute the output. Every set of 8 weights is a filter. Okay? So I'll compute these filters, and then this is linear operation. You still have to compute a function. You're computing a function over the inputs. This function is actually lot more shared parameter, because it is basically using much fewer parameters to compute the function. But you still need nonlinearity, because unless you have nonlinearity, adding more layers is not going to get you any expressiveness. Right? So what happens in this case is I will put the threshold layer here. This is the ReLU layer. Most image recognition networks tended to use ReLUs. In fact, it's very strange. Part of the reason people were using ReLUs is because they thought sigmoid thresholds are hard to control. Because remember, in fact, I remember talking about this like 3-4 years back. If you notice, sigmoid thresholds look like this. And so most of the place, here as well as here, their gradient is 0. And if the gradient is 0, nothing is happening. And so people came up with, oh, if you use ReLU, maybe at least this whole area, half of the area, it will be non-zero gradient. You see what I'm saying? This was actually written even now in some textbooks. It's bogus. You don't need this. If you do batch norm and you do Xavier initialization, it doesn't really matter what your threshold function is. Because it can make sure that things fall in the right region. So ReLU is no longer needed. You can use sigmoids, you can use hyper, tangent functions, etc. But again, in this compressed period, people kept changing their mind. If you're taking physics over a period of long time, for a while you would have thought there is this dense medium called ether through which light kind of goes like water. In those days, the exam question will ask, spell ether correctly. But then after a while, Maxwell showed up and they say, that's all bosoness. We won't talk about ether. That will just be in Wikipedia. We will be talking about Maxwell's equations. This is just happening right now. You actually happen to be alive while these changes are happening, and also you guys are particularly interested in figuring out what is happening. In every research area, things keep changing. This is a particular research area that you're interested in. Okay, so that's the ReLU layer, and ReLU can, and then there's one other new layer that is coming up called pool. This is something that we haven't talked about before. This is max pooling. Typically, pooling essentially means take a region and take some aggregate, just one value out of it. so that the region is now reduced in size. Okay, max pooling will say in the entire region my kernel is looking, just take the max number. How many parameters do we need for max pool filter? Parameters means weights. How many weights do you need for the max pool filter? For a 3 by 3 max pool filter, how many parameters do you need? Yes. Say it loud. None. None. If I give you 15 numbers and I say take max, you don't say I need to learn. It's max. Max pools don't have any parameters. ReLUs basically also don't have any parameters because you already have decided their origin is at origin. So the only parameters are coming from the common layers. And the common layer of 3 by 3 kernel requires 9 parameters. If there are 15 3 by 3 filters, then you need 15 times 9 parameters for that layer. Do you see what I'm saying? This all looks different, but it's the same. It's the same as actually the fully connected network with some extra zinc banks. The zinc banks are actually being done to reduce the number of different weights. Do you see what I'm saying? Okay, so that's basically what happens. So, and by the way, one other thing is, well, we know how to do the backprop over operations like multiplication, addition, 1 by x, etc. Do we know how to do an operation on max? Remember we talked about it. Max is a gradient router. Right? If this last one is x1, x2, max of it comes here, then the gradient coming, whatever is the actual max value, that's where the gradient goes. Because the other guy didn't make any difference to the error. Everything is coming up Milhouse because we have our slow rich uncle who can still deal with all this stuff. Right? Okay. So, example network architecture. Let's just walk through this. One other question that I need to mention basically, let's see. Yeah, one of the other question I need to mention really is the following. That remember when this happened here, this was a 5 by 5 image. When I applied this filter, it became a 3 by 3 image. You may not like that. You might want images to be of the same size until you pull them down to a smaller size. Max pooling will pull them down. Okay? What you want to do is you want to actually get a 5 by 5 image here. Can I do that? Well, you can. You pad. You say there is a big canvas of zeros. Remember how you put your camera, in the old days when you had actual photos being put on into the frames? The frame will have big black background. Somewhere you put the frame, where you put your picture. Then you take a picture of this picture. Right? There will be all this black stuff. That means there are 0 intensities. And then there are normal intensities just for your picture. So you pad. In general, this padding is just like moving average. How many of you are trying to lose weight? Some of you should probably, some of you shouldn't, but I won't necessarily point out. But when you are losing weight, right? When you are losing weight, I'm not looking at anybody, I'm looking the last thing I want is some harassment suit. When you are losing weight, right? When you are losing weight, it's boson-esque to say, today I am 127, tomorrow I am 122, tomorrow, day after tomorrow I am 128, tomorrow something like that. Because every day the weight keeps changing. Because you know why? Actually, you guys know this, you take about 60 liters of water or something, humongous amount of stuff is going in and coming out. In between is the body trying to maintain some kind of a weight. So huge amounts of fluctuations are possible depending upon all sorts of random things. So you take a moving average. Now you take a moving average over 10 days, let's say. What is the average for your first day? You just put a whole bunch of zeros before, or if you are more optimistic, put zero. If you're really optimistic, you should put zeros. If not, you put your target weight probably, and then you start taking moving average over there. That's padding. Okay, so you could do padding, and once you do padding, then you can get the same size of the input to be the output. Right? So for example, in this particular case, I put one layer of padded zeros. Then if I do this 3 by 3, I will still get a 5 by 5 network, a 5 by 5 image. Do I care? Well, it kind of looks nice. In fact, the only reason is that you would like to say that the size of the input is changing only at the pooling layers. Everywhere else it remains the same. Well, all of this is well and good, but remember the following question. There are convolutional layers, the ReLU layers, the pooling layers, blah, blah, blah. What is the last layer? Always the same. Remember I said this, it's always the same. It's the logistic perceptron. That would be a dense, fully connected couple of layers. Normally it's just one, sometimes it can be more than one. Do you see what I'm saying? So you can then say that just as in any fully connected network, you can say the intermediate layers are trying to extract features and the last layer is trying to classify. Here too, all these layers are extracting features which are then used by the logistic layer. And they're just extracting the same way fully connected networks are extracting, except they're using much fewer weights because they're reusing the weights, sharing the weights. Do you see what I'm saying? Now, having said that, because you hung around here, I should give you one more, at least, buzzword. Transfer learning. Why not? Most of these buzzwords are extremely easy once you understand the idea. Right? What's transfer learning saying? If you have, for example, trained a large, very many layered, deep, convolutional network on images, let's say of cats and dogs, etc. And then basically now you get a bunch of different kinds of animals, let's say, or maybe a bunch of X-rays, which are also images. Rather than try to train a completely new convolutional network, you will say, I already have this whole bunch of stuff I trained before. I throw that in, add a couple of a couple of layers at the end, and then of course the logistic perceptron, which will now be looking for different classes, not for cats and dogs, but for you're going to die of this disease versus this disease, and loss error on that. And when